All right, so for our second experiment, we have building the electric motor. This is going to be the really fun one for the kids, and this is something they can certainly take home with them and show their family or their friends, because it's very cool. You start with a D-cell battery, 2 paper clips. Might as well use both of these permanent magnets together, a little square of sandpaper, and 2 feet of this wire, which I would recommend be 20 gauge as opposed to the 18 here, mainly for just being able to use it. Okay, so what I want to do here is I want to basically, oh, you know what, let me put this down. I basically want to make this little guy bigger. So instead of wrapping around a nail, I want to wrap around the battery. And this is why it's good to train the student on wrapping around the nail as carefully as they can so that they get these nice circles, because neatness counts when it comes to making the electric motor. So you can get away with quite a lot with the electromagnet experiment, but we really need this practice to be done early on so that when they get to wrapping the battery 5 times as opposed to 20 for this larger diameter. So there's 4, 5, okay? So now I've got my battery that I can remove. I made my coil. I want to squish the coil down. This coil is going to spin ultimately. I don't want it to be like a spring. I want it to be squished. The way I keep it together is I cinch each side down with the leads. So I take my first lead and I feed it into the middle. Okay, so 1, 2 times, and I straighten out the lead. And see, I've cinched it down on this end. Now, again, this is a little bit too thick of material. Some of the students might have a bit of challenge here bending it because it's a little bit too thick, but 20 gauge would be fine. They'll be in good shape with 20 gauge. All right, so if I were to wrap this over like this, you can see I've got half a turn extra. So I've got 5.5 turns to make this. And if this is how this is gonna spin when I cinch this down, it's gonna be a problem. I'm gonna have half a turn of mass on one end and not on the other. And this thing's gonna spin unbalanced, a lot like a washing machine that has a bunch of towels on one side of the drum. If I ran it this way, I would just be putting the mass onto this side and have the same issue. The solution to this problem is not to run it along the circular part, but to run it straight across. Okay? So what I'm going to do is I'm just going to try to bend this thing over more or less straight across. It doesn't have to be perfect. But the better you can do that, the better across it goes. Let's see. What am I doing here? I'm making such a mess of this. And again, it's working with this thick wire, which is a little bit of a trick. Okay, so there it's straight across more or less. And now I'm going to take this into the wire and I'm going to cinch this side. Okay. All right. And again, we're not looking for perfection, but the more that you can get this thing balanced, the smoother it's going to run and the more impressive it'll be. You can see my first one. You flip over to the next page. I use this as my picture. Like, I'm going to show you, you can get away with quite a bit. That's my first one that I did. And this one's not a tremendous amount better. It's a little better. But this is a little wonky in here. I'm not sure what's going on with this. You know, this loop is pulling down a little bit. It's not perfect. But the point is, what we want to do is we want to bend these leads out opposed from one another so that when you put them between your fingers and you spin it, it spins really smoothly. Like, this feels a little wonky. So I'm going to like bend this down, bend this up, and really kind of make an axle out of this thing. And now it feels like it's smoother in my hands when I spin it. I also don't need this much length on each end. So if I've got my wire cutters out, I can clip it where I've got about 1 inch on each side instead of 2 inches. Don't clip it too short, otherwise it's not gonna fit in our little motor contraption here. It also makes it spin a little bit nicer because you don't have things dangling off the end here. So that's pretty good. So now again, we want to turn this into an electromagnet, because what we're trying to accomplish here is we're trying to flow electricity through these coils to produce this invisible magnet. And the invisible magnet, of course, has a north-south polarity. And we want that north-south polarity to interact with a permanent magnet that we stick to the battery case here, which is fortunately for us, it's made of steel. So it sticks. And on top of that, we have paper clips that also will stick to, oh goodness, they just got linked together somehow. So we we could actually have the battery hold on to our paper clips as well, because everything's magnetized now with these permanent magnets. That's kind of convenient. They'll do this though. Be careful with that. It'll flip like that and frustrate the student. The trick to holding this is between your thumb and your index finger. And you want to hold it straight down where the battery or the permanent magnet's facing down. And ultimately what you want to do is you want to be able to cradle this thing in between the two paper clips, like that. This, of course, is not going to run because everything's coated with varnish still. This is where students run into the most trouble, is where to sand the varnish. If they sand off the entire end and the entire end, this thing is just going to go like this and like this and like this and like this. And it's going to flop back and forth. It's going to quiver. What we need to do is recognize that when the electricity is flowing through these coils, like if it was flowing right now, it would produce a north-south magnet that's going through, similar to the picture that I showed here. So this is the north-south magnet. So let's say the North Pole is sticking out like in the picture, and let's see, we have, I'm gonna flip it over to south. Okay, so there's the south. So if we've got a North Pole and a South Pole, then there's gonna be an attraction. It's gonna pull this thing up, and it's going to want to attract all the way to here. And what we want to do is we want to now turn off the electromagnet so that it continues to spin through until it gets back to its starting point. And then again, there's this attraction that turns back on when the electromagnet comes back on, and it pulls it up again. And it's off, but it's rotating through its own inertia, and it gets another kick. So kick, 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 and it goes faster and faster and faster until it reaches its maximum speed. Okay, that's what we want. If we sand the varnish off of the entire lead, then it's going to feel that initial pull, and as soon as it does, it's going to feel the pull in the opposite direction, and it's going to pull it back and make it go back and forth, and it will quiver until it gets to be about right here. It's just going to go bzzz, back and forth. So we don't want to take all the varnish off of the leads. What we have to do is be careful. We don't let the student put this thing down, face down like this, and start sanding like this. It will set it up where it won't work. We have to hold the loops straight up and down and sand off the varnish off of this half of the lead. Leave the underside alone. Then we flip it over here, and so this is the sanded part. We want this also to be the sanded part. The underside and the underside, we leave it alone. Okay, so I'm going to take my 220 grit sandpaper. I'm going to hold this in place. I'm going to use my finger to kind of be a little backstop here, and I'm just going to sand off the varnish. Okay, now I already did that step for the electromagnet, but I wanted to show you this one because this one's really important. The electromagnet, they can sand the entire lead. It doesn't matter. We're not trying to do some kind of clever switching on and off thing. We're just trying to make electrical connection so we can pick up a paper clip with an electromagnet nail. But this, I want to show you, got to be very, very careful I'm literally using my finger to protect the underside. I just don't want to take that varnish off, otherwise it's not going to work. Now I rotate it over here, keeping in mind this is my dulled up, sanded side, and now I'm going to get this one sanded up just the same way. And I'm going to try not to rush this because I know what's going to happen. If I try to rush, I won't remove all of the varnish I need to remove, and then I'll try to put this thing together and it won't work. And that's what's going to happen. If your students are frustrated that it's not working, it's likely because they didn't get enough of the varnish off to make the full contact. They might have gotten this one perfect, and there's a little bit of varnish stuck here on this one. And if that's where the paper clip is trying to make contact, the whole thing won't work. So it's a little bit tedious in that sense, but if they work at it for a minute or so, they'll get it. Okay, so now I've sanded this down. I want to, once again, twiddle this between my fingers. It doesn't feel quite right, so I'm gonna try to, see that's pretty crooked. So what I wanna do is I wanna maybe like bend it a little bit like this and get it kind of smooth and straight. So when I put it between my fingers, that feels pretty good. Feels fairly balanced. And I think the kids are going to be able to do that part. All right, so we're ready to go. Let's put this thing together. Got my paper clips. I have to scoot them down far enough so that when I put this in here, the loop can rotate without hitting the magnet, okay? But I'm going to hold this thing down, okay? And then I'm going to give it a little nudge. Oh, it's starting to go. See, it's not making great electrical contact. Okay. And this is where the student will be like, it's not working. Okay, that's fine. What you do is you take it back off, you get your sandpaper out, and we were sanding off the very, very top. If we go a little bit from the very top, we go a little like this and sand here. We're still not sanding the underside. We're just sanding a little bit around the side. And then we go from the top, we go like this, and we sand a little bit more of the varnish off of that side. What we're doing is we're guaranteeing that there is adequate connection where the electricity can flow. And we're going to take the other side, we're going to start top, and we're going to go like this. Just make sure that everything is nice and sanded up. And then we're gonna go to the top and we're gonna go this way. And we're gonna just get rid of any little residual that might be there. Good. Testing for smoothness. Not bad. Let's give this a try. We'll get our paper clips first. Paper clips first. Between our finger and our index finger and our thumb. And then I'll load this in. Okay. Make sure I got my fingers here. This won't heat up, by the way, as much because there's so much on-off going on. But let's see here. Is it going? It's kind of going. Can we make it better? Oh yeah, we can totally make it better. So if you notice, it's kind of flopping. It doesn't look particularly balanced. So I could do a better job of balancing it. So this is where it's a little finicky. We just want it to be a nice, smooth system. All right. Try it again. Okay, so let's just take this and see if we can get it to go. So we put it back into our system here. We've got a little bit of space here between the loop and the magnet, and we give it a little kick. Let's see if it'll go. And there it goes. Okay, and so it's spinning pretty good. And the kids are gonna love that. All right. So we finished things up by talking about what's going on here. When the battery sends current through our loops, the loops become an electromagnet. This electromagnet either gets pulled or pushed by the permanent magnet that is stuck to the D-cell battery. As a result, the loops feel a rotational force called a torque and begin to spin. But we only want the loops to get a kick at the right moment. That's what we were describing before with the varnish and sanding off in the right place. Otherwise, it's just going to flop back and forth, and we went through the process of why that's the case. So what we need to do is turn off our electromagnet and let the loop spin through a full rotation before we turn it back on for another kick. And so I try to make I try to put it in a little visual sense of like kick. A little bit of time goes by, another kick, another kick, another kick, another kick. And then goes kick, 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 kick. And it's like going as fast as it's going to go. The motor spins until it hits that maximum rotational speed. And the reason it doesn't keep spinning faster and faster forever, but instead reaches this maximum speed, has to do with this funny law of physics called Lenz's law, which is something we're not going to get into, but we just have to let the students know, or we should, that there's an upper limit on how fast an electric motor can actually freely spin. So at this point, we congratulate the students. We say, now you built an electric motor for the first time. Go ahead and take this material back home and play with it and see what you can do with it. You might want to try making a similar type of motor using a AA battery with smaller loops. We might want to do 6 loops, 7 loops, maybe just 3 loops. See what you can do to make this thing perform differently. It might be a little bit better if it's got 3 loops, just because you can control the shape of those 3 loops better than you can maybe 7 or 8. So there's probably a sweet spot for that. How much varnish can you remove before it doesn't work anymore and just starts flopping back and forth? You could have the students add a little cardboard fan blade to the end here. As it's spinning, it's driving the fan. And then the final thing that we can do is we can say, we can kind of tie this all into this idea of forces. And this is a really good one, because what we've been saying is that the magnet that is being produced by the electromagnet, this sort of invisible magnet, is being pulled by the permanent magnet. We could also say, and be completely accurate, that the electromagnet, the invisible magnet, is pulling on the permanent magnet. And that's the case. So the permanent magnet pulls on the electromagnet equally but oppositely to the way the electromagnet pulls on the permanent magnet. And this equal and opposite force pair is what makes up Newton's third law, which most people quote as every action has an equal and opposite reaction. Not the best phrasing, because it's not like one thing pulls on the other and then suddenly the other thing says, oh, I better pull back. It's that these two forces develop at the exact same time. They're pulling on each other equally and oppositely as a force pair. And you can use that to go into all sorts of other discussions. One of the classic ones is that we all know that Earth is pulling down on us to keep us stuck to the Earth. But the amount of force that Earth is pulling down on us is the same amount of force that we are pulling on Earth. You know, our massive bodies are pulling on Earth with an equal and opposite force. It kind of messes with your mind trying to think about it that way, but that is in fact the case, that these force pairs develop in accordance with Newton's third law. So if you want to float that out there to your students, that's a really good application to say that these magnetic forces are equal and opposite to each other, and this is what's driving our electric motor to rotate. Very cool stuff. We can talk more about torque and other things as well, but for the purposes of this experiment, I think the students are going to come away really happy. Thanks for listening.